video, we are going to take a look at BCA tables and how they can be useful in demonstrating or illustrating what's happening in a chemical reaction without actually having to draw out the reaction on the particle level. So what you'll definitely need a balanced equation, and then you will need essentially a chart that has a before row, a change row, and an after row. And then we're going to just abbreviate that as BCA moving forward. The before is before the reaction occurs, what is present. So there'll be no products beforehand, you'll just have your reactants. Your change row is what's happening during the chemical reaction, so which molecules or atoms are actually participating in the chemical reaction. So how many reactants are being used up, how many products are being formed. Then the after row is going to be illustrating what's actually present after the reaction. So the products will now be present, but will there be any leftover reactants that weren't able to react? So in this case, you always need a balanced equation. We're going to look at the reaction of nitrogen plus hydrogen going to ammonia, NH3. Here are N2 and H2 are diatomic. Now in this case, we'd have to figure out how many N's, how many H's are on both sides. And in this case, we aren't looking at the picture. We aren't looking at a chemical picture. We're not looking at any given information. We have to go lowest terms to make this equation meet the conservation of mass. So in this case, the balanced equation would be a 1, 3, 2 relationship. So again, those big numbers in front, the coefficients, stand for the number of those formulas to balance that out. And then in this case, we've illustrated that the nitrogens and hydrogens are equal on both sides. So in this case, if we were to look at the balanced equation down here, those big numbers again kind of have a ratio of what's going to be occurring in that balanced equation or in that reaction. So in this case, it's a 1-to-3 ratio. Here it's a 3-to-2 ratio, and then here it's a 1-to-2 ratio. So we have a particle of a picture of what kind of a sample of nitrogen and hydrogen. So we see nitrogen in here, and we see hydrogen. Now, we've either kind of circled up the batches, or we said we're going to lasso or circle up the molecules or atoms that are going to participate in the reaction. So on the reactant side, we have 1 N2 and 3 H2s. So I'm going to go ahead and circle 1 N2 and 3 H2s, which I have here. And that's going to produce 2 NH3s according to the balanced equation. So in order for this reaction to occur, 1 N2 and 3 H2s need to come together in a small space, and they actually need to collide all at the same time and in the same orientation for this reaction to occur. So these four molecules will hit one another. Bonds are gonna break. They're gonna reform, and then we're gonna reform these 2 NH3s. So notice the conservation of mass is met here. We have 2 N's here. We have 2 N's here. We have 6 H atoms, and then we have 6 H atoms over here. Notice that this H is purple and this one is yellow. It's still the same element. Okay, the color coding is going to relate it to the balanced equation. That the 1 is nitrogen, so I color coded those blue. The 3 H2s are yellow, and then we're going to produce 2 NH3s. So I was able to make one batch of this reaction, but I'm going to go ahead and try to make as many as I can in this picture. And in this case, I'm able to make 4 batches of this reaction. I circled up another 3 H's and 1 N, or I guess 3 H2s and 1 N2. That would form 2 NH3s from the balanced equation. Another 3 H2s would collide with an N2. That could go ahead and react to form 2 more NH3s. And then again, we have a 4th batch that can make these other 2 NH3s. Now you'll notice that we have 1, 2, 3, 4, 5 N2s left over. There are no H2s to react with it, so therefore they're going to be left over in our product side. They're still going to be present because the conservation of mass has to be met. So all the ones that we have highlighted here and circled are going to react according to the balanced equation, but we will still have some leftovers. So here we have 9 molecules and 12 molecules, and that's not so bad to draw, but if you get any more than that, it gets quite cumbersome. And we wouldn't want to be drawing endless reactions every time, or endless amounts of these every time we want to take a look at a chemical reaction. So we're gonna put this picture into a BCA table. Now I've shrunken this picture. I know we can't necessarily read it that well, but we can see the highlighted versions from before, that the 1N2 is blue, the 3H2s are yellow. So the before row, we are looking at before the reaction. So although in your picture we might be able to see the products, we are looking at before the reaction actually occurs. So in this case, I'm going to count up how many N2s I have. So in this drawing, they're both blue and white. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 molecules of N2. And I have 12 molecules of H2. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Notice I didn't put 4 here. A misconception is to say, well, I have 4 3H2s. We are looking at just H2 formulas, and we have 12 of them. And then your products will always start with 0 because it's going to be before the reaction occurs. Now, we have a change row and an after row. The change is going to be everything that reacts or is produced. So anything that we've circled up. So in this case, we've used up 1, 2, 3, 4 N2s. So I've used up 4 molecules that are going to react. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H2s that are going to react. And over on my right side of our picture, we have formed 2, 4, 6, 8 NH3s. It's always going to be subtracted on the left-hand side for my change. It's always going to be a plus sign for my right side because we're using up the reactants and then in order to form the molecules or atoms on the right-hand side. Our after becomes a math problem. 9 minus 4 equals 5. 12 minus 12 equals 0. And 0 plus 8 is 8. That should also match my after picture. I have 0 H2s present. I have 5 molecules, 1, 2, 3, 4, 5 N2 molecules left over. And I have 8 molecules of NH3 in my after picture. Notice the number of total molecules before and after don't necessarily have to match because each particle or each molecule might have a different number of atoms in each one. However, if you added up the total number of atoms on both my left picture and my right, they would be equal. One thing I want to highlight here is that the change step matches the balanced equation ratios. So in this case, the N2 and H2 is a 1:3 ratio. Each one of these had 1 N2 and 3 H2s. So once we add up all of the N's and H's that we used 4 and 12, then it's still in a 1:3 ratio. 12 is 3 times 4. Notice the 3:2 ratio between the yellow and the purple. For every 3 yellows, H2s here that I use, I'm going to form 2 NH3s. 12-8 relationship is the exact same ratio as a 3:2 ratio. And notice a 4:8 ratio, 4 N2s to 8 NH3s, matches the 1:2 ratio according to the balanced equation. Every time I use 1 N2, I'm going to form 2 NH3s when that balanced equation is run. Notice the before row does not match the balanced equation. The after row doesn't, but the change will have the same exact ratios as the balanced equation. So what happens if we actually don't have a picture to go off of? So in this case, we have 9 molecules of N2, 12 molecules of H2. So we're going to look at the exact same problem, but see how we can relate it to our BCA table without looking at our picture. So in this case, we have 9 molecules, 12 molecules, and we always know our product will be 0 molecules to start. Now, how do we know which one's going to run out? At first glance, we might not be able to recognize it. It's kind of a guess and check. I'm just going to go with the smallest number, or the one on the left. In this case, let's say we're going to try to use up all our N2s. So we have to figure out how many H2s we would need in order to completely use up the N2s. So in this case, I'm going to take my 9. I know it's a 3-to-1 ratio, so I always know that I need 3 times as many H2s as I do N2s. So in this case, I'm going to take my 9 and multiply it by 3 over 1 because that's my ratio here. Now I multiplied it by 3 over 1 instead of 1 over 3 because I know that I need more H2s than I do N2s. So in this case, I need to multiply by a fraction that's greater than 1. So 9 times 3 is 27. So again, notice the 9 and 27 are in a 1-to-3 ratio. Now, if we actually look at our picture, we had 9 N2 molecules, but we don't actually have 27 H2 molecules. We've used up all our H2 molecules, that we don't have enough H2 molecules to completely react with the N2s. And you'll see it in the BCA table as well, that we only have 12 to start. We can't use 27 molecules if we only have 12. So we must not be able to completely use up all 9 molecules of N2, and we saw that in our initial picture. So we must actually have used up all our hydrogen. So in this case, we're going to actually flip it. Now we're going to completely use up the 12 molecules of H2, but then we have to work backwards. How many molecules of N2 would need to react to completely use up the 12 molecules of H2? In this case, again, I know it's a 3-to-1 ratio, so I'm going to multiply by 1/3 because I need this number to be 3 times the N2. So I need 12 is 3 times 4. Now how did I get there? I multiplied by 1/3 because the 12 represents the hydrogen. So I know I'm going to have to use this number in my ratio. And I'm trying to figure out N, so I know I'm going to need the 1 from this ratio, the 1 from the N2. So I know I'm going to have to use the blue and the yellow, the 1 and the 3. And I know I'm going to have to get a smaller number than 12 because again we have 3 H2s. We're going to the N2, which is 1. So I need this number to be smaller than this one. So I'm going to multiply by a fraction that's less than 1, which is 1/3. 12 times 1/3 equals 4. So again, notice the 1-to-3 ratio. And this is actually what we saw in our picture, that we used all 12 molecules of H2, and we only needed to use 1, 2, 3, 4 N2s. How come? Again, because I was in a 3-to-1 ratio in order for that balanced equation to work out. Now, many people get stuck at kind of going to this next change step as far as what numbers to use. We just have to stay in the change step. We can't be bringing things from the before section as long as we use a number in the change step. So I typically use the one that's going to run out. So I'm going to start with my 12 molecules. I know it's going to run out. And I'm going to relate it to my NH3. So in this case, I have to look at the ratios, and that I'm going to have a 12 here. That's going to be representing that, okay, I have 12 hydrogens, or 12 H2s, I'm sorry. And in this case, I want to figure out how many NH3s. Well, I know it's a 2-to-3 ratio. And in this case, if I remember, for every 3 H2s, I need to form 2 NH3s. So I'm going to have to use either a 2/3 or a 3/2 ratio. In this case, I chose to do a 2/3 because I know I need less NH3s in my equation than I need H2s. For every 3 H2s, I need 2 NH3s. So I need to multiply by a number that's less than 1. So 12 times 2/3 equals 8. Notice I can check my work because the whole change step needs to match the balanced equation ratios. We've just calculated this. We already calculated the 1-to-3 ratio here, but let's double check our last one of N2 to NH3. That should be a 1-to-2 ratio. For every 1 N2 that we use up, we should form 2 NH3s in our equation. In this case, we used up 4. We formed 8. That is a 1-to-2 ratio, so it looks like my numbers are good. Now, some people get kind of confused as far as, well, do I have to use 12 here? And the answer is no. What we could have used 4. And why could we have used 4 is because we could have related it with our N2. So in this case, if we said, well, we're going to use up 4 N2s, how many NH3s would we produce? Well, we see it's a 1-to-2 ratio. So somebody might kind of look at this ratio and think it's a little bit easier to work with. Well, if I use up 4 N2s, that 4 is coming from here. That's the blue number 1, so I know I'm going to need that in my ratio. I'm trying to figure out NH3, which is our purple, which is my 2. It's going to be a 2/1 ratio because I know I need twice as many NH3s compared to N2s. So 4 times 2/1 equals 8. And yep, indeed, that's the exact same answer I could have gotten if I started with 12. But because I started with 12, I needed to use a different ratio to get there. It's important to note that 9 does not show up here because that's in the before row. In order to use the change step, we do need to use numbers in the change step to figure out the other change molecules or atoms. Okay, so I'm going to delete that and I'm going to kind of go back to my original one here. So we have our change step. And in that case, we could figure out our after. Again, it's a math problem of 9 minus 4 equals 5, 12 minus 12 equals 0, and 0 plus 8 is 8. But often that change step is what kind of hangs people up. Now, these problems often ask for mass. So, for example, a question could ask, what is the mass of the NH3 formed in the chemical reaction? So in this case, we have to be a little bit careful. We aren't using the balanced equation of the coefficient of 2. We first have to figure out the mass of 1 NH3. So I'm going to go ahead and do that. And we're going to need the periodic table to do that. So I look at my 1N atom, and I multiply it by the mass of 1N from the periodic table. I have 3 H atoms in my NH3 times the mass of one of those H atoms from the periodic table. I add that up. That one molecule of NH3 is 17.031 AMUs. But in this case, I formed 8 molecules. Okay? Or in my picture, again, I formed 8. And again, we're using our BCA table, so we don't actually have to draw all those out. Now, in this case, we formed 8. So my calculation would be, I have my 8 molecules, and I'm going to multiply it by 17.031 AMUs. That's how many AMUs is one molecule, so I kind of put a slash molecule here. So 8 molecules times 17.031 AMUs per molecule, I end up getting 22.007 AMUs of NH3. Now these problems could also ask how much mass of nitrogen was left over, so I'd have to start with my 5 molecules of N2. Could ask how many what's the mass of the hydrogen that was used, so then I would need the 12 molecules of H2 here. But again, it's important to note, when you do make this mass calculation, you are not looking at the coefficient of the balanced equation. You're finding the mass of the formula and multiplying by how many molecules that you have. A variation of this problem is when sometimes the question will say something is in excess. When something is in excess, that just means that we have more than enough of it for this reaction to occur. So in this particular case, we had more nitrogen than we actually needed. We could have ran more batches of this reaction if we had more hydrogen. So sometimes we say, well, nitrogen would just be in excess. And so that means hydrogen would be our limiting reactant. So if a problem said, well, we're going to react 12 molecules of H2 with an excess amount of nitrogen, that just means that we don't actually care how much nitrogen is there. We just know that we have plenty of it, or lots of it, more than enough of it, and we're just going to put excess here. Now, when we actually make our BCA table, that actually makes things a little bit easier. We don't have to determine which one's going to be used up. That means that we know that the hydrogen will be used up, and then the rest of the problem is going to be exactly the same. There's just no debate what's being used up. We can still fill in the change step for the excess reactant and figure out how much we needed of it, but afterwards we can just put it in excess again. We don't exactly know how much is there, we just know that we have it left over. So in that case, this would be our excess reactant, something that has the molecules or atoms left over, and this would be our limiting reactant. It's going to limit how much NH3 that we can produce, and that's going to be that we're down to 0 here. So again, in kind of a conclusion here, that our BCA table is a way to represent what's happening in the chemical reaction. Our first row is going to be before the reaction occurs. The change step is going to match the ratios according to the balanced equation, and those are the molecules or atoms that are going to be participating in the reaction, and we have to use the ratios to get there from the balanced equation. And then our after is going to be what's present after the chemical reaction.